Assalamu alaikum viewers. This is Taimur Ali Khanzada and in today's video I will be presenting you our final year project which is titled as Optimizing Hardware in the Loop Setup and Digital Control for Teaching Steady State and Dynamic Behavior of Power Converters. So first of all let me introduce you our FIP teammate Mr. Sadakat Ali on the screen and Mr. Shiraz Umar and myself Taimur Ali Khanzada. And before starting over this video, I will be thanking my supervisor Dr. Jamshed Ahmed Ansari and co-supervisor Dr. Jahangir Badar who helped us in completion of this project. So let's move to the details of this project. So this is the outline we will be following in our today's video. First, introduction, then the motivation behind the project and problem statement, then a little bit literature review, aims and objectives, then methodology, results and discussions, outcomes of the projects, and conclusion and future recommendation. So first of all, I would like to introduce our project. What is HIL setup and why we have chosen this. HIL setup basically is a hardware in the loop setup which is used for the real-time manufacturing and design and development of power systems and power converters. And it is efficiently used in the renewable energy, and it is very important for practical hardware design. And HIL setup enhances the skills of students in troubleshooting, and it fulfills the theory and practical gap in academia and industry. And it also provides a lot of research opportunities to the students if they are being taught on HIL setup, and it gives us a hands-on experience uh, of real-time engineering problems and design to students. So motivation behind the project is to that traditional education lacks hands-on experience, hindering grasp of complex power systems. Realistic testing environment crucial for new control strategies and designs, which HIL setup provides as well. And it enhances students' learning with deeper understanding and retention through real-world interaction. It enables design and testing of more efficient and stable power systems, contributing to achievements in the field. Problem statement. The current gap between theoretical power systems education and limited hands-on testing hinders both student understanding and researchers' development for real-world control strategies. In literature, you can see the references are given here that each reference targets each problem and its solution with HIL setup. That in pedagogical approach aspects, you can see that theory-centric environment has limited hands-on experience, which provides students challenge to apply knowledge, which is a lot of knowledge consumption and a less of application of that knowledge. So fill setup provides a deeper understanding of such systems. Similarly, it provides a learning environment which is a dynamic interactive labs with real-time feedback, and it provides hardware resources as if you are designing a power converter system or any power system on real prototype hardware, you will get it very costly. So you can easily design that system on HIL setup without arranging specific hardware. So it provides increased access to power electronics education. So yeah, from here you can get a lot of access and a lot of dynamics to power education, power electronics education. Continuity, it can also provide the gap between continuity to the undergraduate study to graduate level studies. Overall impact, if we go for traditional methods, limited practical application hinders innovation and inadequate preparation for industry demands. So what HIL setup provides bridges theory and practice, fosters innovation, which prepares students for the evolving field of the power electronics. So let's go to the methodology and all or other details of this power steady state and dynamic behavior of power converter study on HIL setup. So our aims and objectives are to implement advanced digital control techniques to improve the performance and stability of power system within the HIL framework, create a comprehensive educational module using the optimized HIL setup and digital control methods to enhance the teaching of power systems, demonstrates the application of optimized HIL setup and digital controls by applying them to real-world power system research problems. So in methodology, in our all presentation there. The methodology is divided into two parts: offline simulation and one is online simulation. In offline simulation we have designed mmc converters on MATLAB and have applied a comparative analysis of NLM and SPWM techniques. And in real-time simulation, a boost converter is implemented on HIL setup PXI, and an induction motor speed controller is designed on GPIC for real-time testing of power converters dynamic behavior and control of induction motors speed and with testing other parameters. So let's discuss about some of aspects of NLM and SPWM. In NLM, you have a reference signal and a round function, then a capacitor voltage balancing algorithm, then you generate gate pulses. Here you can see a reference sinusoidal signal is taken and nearest levels are generated through this using the algorithm, nearest level algorithm for generation of the gate signals. In SPWM, you take a sinusoidal signal as a reference and take multiple carrier signals as comparison of the reference signal. Here you can see a MATLAB code is present here in which a sinusoidal signal is taken and a carrier signal for a gate signal is taken in the reference to if sinusoidal signal is greater than triangular carrier signal, then a gate pulse will be generated. A similar waves methods are used for other carrier signals, but one thing is to notice that each carrier signal is 2n by 4 degree apart from each other. So in real-time methodology, you can see a computer PC in which we control the software and provide Mario control, and Mario controls the PXI circuit. So this is our hardware in the loop circuit, and here is the interface we are seeing: DC to AC inverter control desktop file. This is our GPIC board which is used for the control of our induction motor, three-phase induction motor. So let's discuss the results. First we are discussing the offline results we have taken and what we got from them, and then we will be moving towards online results. In offline results we have simulated 5 different configuration of MMC modular multi-level converter on MATLAB, and on each configuration we have applied SPWM technique and NLM technique as well. Here you are seeing that results when n is equal to 24, any 24 mmc submodule. So THD is 5.57%, and for NLM and for SPWM THD is 7.85%. Here you can see the THD content of NLM is better than SPWM. In next slide you are seeing that for n is equal to 50 number of submodule, NLM is giving us 3.69% of THD, while SPWM is giving us 5.72% of the THD. Here also the NLM is performing better than SPWM. However, when number of submodules of MMC are increased to 200, here you can see that 2.91% of the THD is generated by NLM technique and 0.38 technique is generated by SPWM technique. And this was the point where we got a distinction between the SPWM technique and NLM technique, which is very important. So here is a table for n is equal to 4 number of submodule. The THD generated by NLM and SPWM are presented here, and you can observe that while till 50 number of submodules, NLM is performing better than as compared to SPWM. However, when number of submodules are increased to 200, here you can see that NLM is not performing better than SPWM. Here the THD content of SPWM is less and the THD content of NLM is greater. So now you can, from here you can conclude that NLM performs better on lower number of submodule and SPWM perform better on higher number of submodule of MMC. So let's now move to our real-time simulation results. In real-time simulation results, we have open loop control of motor and closed loop control of motor. So here you can see the interface that PWM frequency is applied 2000 hertz, and open loop output frequency what we want RPM is 1800 is set, and modulation index is taken to 1. But here you can see in open loop, if we have set the RPM at 1800 but we are getting the actual RPM 1785. So here is a little difference between the set point and the real RPM of induction motor. Now we have taken an open loop circuit. The RPM is 1000. At 1000 RPM you are getting 994 RPMs. Similarly, the RPMs are tested to 1500 RPM. So at 1500 RPM in open loop system you are getting 1493 RPMs. And for 2000 RPM you are still not getting the actual RPM in open loop circuit, you are getting 1990 RPMs. So then after taking readings on multiple RPMs in open loop system, we have tested the effect of modulation index on the waveforms. Here you can see the modulation index is taken as 1, and you are seeing that complete waveforms are being generated by the converter. But if we undermodulate it, we have taken the modulation index 0.5, you can see the size of the waveforms is decreased. And in same way, when we have highly under modulated the converter, so you can see that at 0.2 the waveforms are even less than previous. Now we have tested the effect of modulation index by increasing the modulation index to 2, and which is also referred as over modulation. In over modulation you can see the waveforms are clamped and not generated sinusoidally. So these were the effects of modulation index on our power converters voltages which are applied to motor. And now the effect of frequency is analyzed in open loop, that what is the effect of switching frequency when we have applied 500 hertz frequency, and you can see the shape of waveforms is distorted very largely. So again when we increase some frequency to 1000, you can see now there is a better waveform as compared to 500 hertz. And when we applied 200 hertz frequency, you can see now the waveforms are still better, more better than 1000 hertz frequency. And as we know that as much as we increase the frequency of the power converters, we will get the better sinusoidal waveform. And here you can see at 3000 hertz of frequency you are getting a very well sinusoidal voltage waveform with some distortion, but they are very well and better than other frequencies. And if we increase frequency more to more, we will get a pure sinusoidal waveform of the converter. Here is the testing of the fault. So you know when a motor is operating at 1800 rpm and suddenly we change a huge difference between the rpm, as we have changed from 1800 rpm to 500 rpm, our motor went to fault, and we have observed this fault on phase IU current A. So you can also test about the occurrence of fault on induction motor in real time. Here comes the closed loop results of our induction motor. Here you can see the value of Kp and Ki, and these values are taken on hit and trial basis. And you can see now we have set it the RPM at 1800, and you are getting the actual RPM at 1800 in closed loop, while this was not true in the open loop results we have shown before. So similarly we have taken different RPM readings. At 1000 RPM you are getting almost 1000 RPM, at 400 RPM you are getting 400 RPM. Similarly in closed loop at 2000 RPM we are getting 2000 RPMs of the motor. And again we have tested the effect of frequency, switching frequency in closed loop, and you can see at 100 hertz your switching frequency is not performing well, and you can see at 2000 hertz your frequency is very good, and at 3000 hertz your at frequency 3000 hertz frequency your waveforms are very well. These are the similar results as compared to, but this is not in open loop, these are in working in closed loop. Here we again tested a fault in closed loop at 2200 rpm to 1000 rpm, and suddenly our motor went to fault as our current reaches to 10 ampere. Here is the our hardware diagram of motor control. You can see this power supply is given to this GPIC circuit, and this is the power supply AC supply which is given to here in converter, and we are getting a three phase. This power supply is AC, and this AC power supply is given to this power supply, and from this power supply we are getting DC voltage, and this DC voltage is given to this converter chip, and from this converter chip we are getting three phase voltages which are given to this induction motor. And here is a rotary encoder which is given here for the control and communication purpose, and this power supply is given to this GPIC. So this is our overall circuit of induction motor control, and as we have discussed the results before to you. And what outcomes of project done, we have written a conference research paper on comparative analysis of phase shift carrier PWM and NLM in modular multi-level converters, and now we will be writing on our second paper for awareness and promotion of HIL setup, optimizing hardware in the loop setup and digital control for power system teaching and research with these results. So in conclusion, we have this project explored hardware in the loop simulation for power system education, or simulation compared modulation techniques for MMC systems. Online simulation various circuits such as boost converter motor control systems on HIL setup. These experiments showcase the benefits of HIL for students and researchers. Future recommendation we will be given that this topic can be taught on HIL setup for the efficient usage of HIL setup for teaching and research purposes. And these are the references given. Oh, and thank you very much. Must follow our YouTube channel and watch our videos, and in any case of query or discussion you can ask in the comment section. Thank you very much.